Hey, I'm going to get started here. Hey everyone, welcome to another episode of the Haskell Study Group. I'm your host, Ram Vedam, with Atlanta Functional Programming. Apologies for last week's sudden cancellation. Some stuff came up and I was unable to actually do the stream. Today we're finishing up our discussion of the section on algebraic data types. Specifically, our topics are going to be discussing is we're going to be discussing function types and some specifics about function types that we haven't actually covered. We kind of indicated it in the last couple of weeks. Last time we discussed algebraic data types in general, and this is in general when we were talking about kinds. But this is about functions in general, and we'll get into that specifically on how to calculate for a function that represents a mapping between one type A to another type B, the representation of the inhabitants of that particular type, which is actually normally written as a pair input comma output. Okay, this kind of has an interesting mathematical result. It turns out that because you have this distinct mapping, you can use exponentials to go and compute the actual inhabitants of that given function type. Okay, and we'll go through some examples of that today. Additionally, we're going to be talking about higher kinded data types. We've talked about kinds before, and we're going to be talking about essentially multi-argument kinds, which will end up falling under the umbrella of term higher kinded data types. Also, we're going to, now that we've kind of introduced this notion of what an algebraic data type is, we're going to finally have the discussion on why lists themselves are considered polymorphic data types. I've introduced the concept that list wasn't a polymorphic data type earlier on, and we've kind of went through this kind of discussion of what a polymorphic data type is, at least at a very simple level, but we never actually talked about what the specifics are with respect to Haskell's approach to actually designing polymorphic data types, and we're going to end up talking about it with the guise of talking about lists specifically. But the principles around list itself and how it generates its definitions can be applied to other discussions, and we're going to hopefully, time permitting, go through the binary tree example that was discussed at the end of chapter 11 inside the Haskell book. A couple of things that I wanted to kind of discuss about this is mainly related to the function stuff, because a lot of that stuff is related to some theory, essentially category theory, and the exponential types written on top of category theory, and how exponentials can be represented in a category using some tricks. I recommend for folks who are interested in this theoretical foundation to look for books related to category theory. A couple of ones that I've personally read. One is Bartosz Milewski's Category Theory for Programmers. There was actually a discussion done by the Programming Languages Virtual Meetup. We just finally finished the first reading of that book. I honestly recommend that to folks who want to get a good, nice overview of it. But if you want more of a more mathematically grounded version, because that book doesn't go through a lot of the proofs and results from category theory. There's also Category Theory for the Working Mathematician by McLean, and I think that's another book that I think other folks can start. I started just reading that, and that's for more of a thorough mathematical foundation on the subject matter. Now, you don't need to necessarily know category theory to pick up some of the results that we're going to be discussing today, but it can provide more of a, certainly more of a, an understanding that would help you either adopt certain design decisions or certain design patterns, or better yet, especially when it comes to Haskell and its notion of type classes and implementing functors, applicatives, and monads, and some of the higher monoids and semigroups and things like this that are categorical results. And these are all already defined as type classes already inside Haskell. Understanding this theoretical foundation will allow you to leverage those more effectively. I know some folks may disagree with that statement, and we haven't covered some of this material yet. But as we get to those points, at first pass, when you actually look at solid examples, when you're using functors, applicative monads, it may look like that you are simply, in the Haskell sense, implementing a type class instance so that you're registering those rules on how that particular interface is being implemented for your type, but there is actually some solid foundational material behind that, there's reasoning behind that. So let's get started. First things first, let's talk about function types, okay? We've already looked at functions in many different ways. You know, you have a function f that takes in an a and returns, a function f that takes in some type a and returns a type b, okay? And these are just type variables and end up being leveraged. But one question you may want to ask yourself is given a set of inputs of type A and mapping them to a set of outputs of type B, how many results can we create? All right. This is kind of the question that it sets the backdrop in this representation. Okay, what do I mean by that? Well, let's take some very some simple examples here. Okay, and obviously I'm going to start with bool because that's a pretty simple, straightforward example already built in to the function into the language. Okay. And this is kind of the one that most people are introduced to understand some of those results. When you are generating results, okay, let's say that we have a function f that takes in a bool and returns a bool. The first thing you have to think about is for each result in the input, what results can you get from the output? Okay, so we have two results in the input, either true or false, okay? So additionally, given true, in the way the function is written, we can either get true or false for the first one as an output, or map true or false as an output for false, which means we have a total set of 4 pairs, okay? These may not be, some of these results may not necessarily be valid results with respect to the actual function that we've defined, but they are valid inhabitants of that type. They are members of that function type that we defined of going from bool to bool. This is a very important thing to note because of the fact that when most people start looking at functions and mappings, they're looking at the set of valid results that are representing this type. That's not what you want to look at when you're looking at data types, because the set of valid mappings, of course, will help you test your code. But when you're testing your code, you don't want to just check the valid mappings. You want to also check the invalid mappings too as well. So you want the whole set, if you will, for lack of a better term, of all the inhabitants for that particular type mapping, so that you could go and take care of and probably even exercise in your code on those things. So we have these 4 types, right? Well, if you actually look at this, right, these 4 types is nothing more than we've taken the output, okay, which is bool, okay, and we actually just simply raised it. Okay, so the cardinality of the output, okay, which is representing the set of all values in the set bool, and we raised it to the cardinality of the input, okay, because for each input type you get a set of output types, all right. This is the same as obviously the equation b to the a, okay, but this is a simple example, and unfortunately, because bool is such such a special number, because 2 plus 2, 2 to the power of 2, 2 times 2 are all the same result. It doesn't really illustrate some of the stuff that we talk about. So the book kind of gave one example that I think we'd want to go through. Although I hate the name, so I'm going to change the name just a little bit. They named it quantum for some reason. I have no idea why. I guess that may be because it is a response to a question. I don't know. Quantum, when I think of quantum, I'm thinking of quantity or something from quantum mechanics. But, that is obviously may not be something necessary. Because it literally means something has been discrete. Okay, so I'm going to just simply change this up a little bit but to illustrate the point, but it is something to be aware of. So this is kind of referencing kind of chapter 11, section 15 on function types is no, sorry, section 14, which is and the example, quantum example. And it's kind of the same idea. Suppose you're building a question response system, and you want to kind of have a response, okay? And you might have, say, a data definition called response, and it might take in 3 different values. It could either be yes, or no, or both, okay? And we're going to be deriving this as being EQ and show, just so that we can actually go ahead and use this later on for some of our things, okay? So there's 3 different ways that you can determine, what you are actually leveraging, okay? The first one is you're dealing with the sum type example, okay, sum type cardinality, okay, of a given function type, okay. Here, you're going to be ending up leveraging essentially probably like the iter type, okay. So just to show you what this is, if we do either, you'll see that either is nothing more than a left or a right, okay? So we're going to be having to deal with cases for left or right, okay? When we define this, we could certainly see, well, how many different either types can we have in this output, okay? Well, let's talk through it, right? You have, let's say that you have response 1, okay? That's going to be either response or response. And let's say that we take in, okay, nothing more than response 1 equals right, yes, okay? Sorry. Here, we actually have one value that's represented as a valid value. Now, we could certainly make this, let's do this as, let's rename this as yes, okay? That's for showing you the 3 cases. And we might have, 2 additional cases here as no. Sorry, let me go ahead and do this. No, or both. And these will return no and both respectively. Okay. Each of these is a valid either type. Okay, if we actually go and look at the type information that's being provided by the underlying, sorry. Okay, there we go. REPL here that we have, so let's say the type of RES, we could see all 3 of these are actually valid members of either response, okay? Now, but this isn't the complete set, right? This isn't the complete set of responses that are members of the either response type that we've just constructed, okay? Remember, this guy here is either response is an actual concrete type, and this higher this type, which we'll be discussing, is technically a higher kinded type, okay, because it requires 2 additional concrete types in order to be actually fully applied in a concrete instance of that type to be constructed, okay? Higher kinder types we'll be discussing later on. If we end up, obviously partially applying it, we have this ability to actually get the same thing. So let's finish this off. So if we have this, obviously if we have the fact that we have a left and a right in the either type, we naturally have now an additional 3 more values that we need to take into account for, right? And that is, here we have the left side of all these, okay? So now we have the right side and the left side. So what is the total number of values? Well, you could pretty obviously guess here. The total sum here, the total inhabitants, is just nothing more than 3 for the right side plus 3 for the left side, which means we have a total set of 6 inhabitants for this given type instance, okay? That this fully realized type has 6 members, okay? And you have to account for all 6 members. This sometimes is necessary when you're building applications to know about it, because there may be a situation where you may need to exercise every single possible type. Now, obviously, for larger types and primitive types, that is not only a ridiculous requirement. It's an impossible requirement for some types. For example, fuzzing out and testing every integer of the member of the 64-bit integer class. Right? That's just good luck. I don't think you have the time in the world to test every possible integer of it, even as fast as you're getting it. That would be pretty impressive if you could. Let me know how that works out. For something, say though, for like nowadays with computers being as fast as they are, say like 2 to the 16th, which is only like 65,536 integers, you could possibly go ahead and test that pretty fast now, probably in minutes, maybe in the worst case, maybe a half hour or so, or something like that. And you can use that to actually go and verify and try out different kinds of things. The point of this kind of calculation, though, as we will soon see when we're dealing with function types is that the mapping calculation will give you kind of an indication on what to test. All right, let's continue on here. We have this sum type one. Let's try a product type. Well, obviously we can change this, right? We could with the product types we have a different thing, right? Product type is usually represented as a pair, and we will be dealing with this using and the Cartesian product is right to actually go and compute this. So with this product type calculation, inhabitant calculation, we're going to be dealing with essentially the Cartesian product, which is going to be three values for the first type of thing. So let's say that we're going to be dealing with, let's say we're going to be dealing with pair one is going to be of type response. Okay. Pair one is going to obviously have this equal to yes. Okay. And you can see very quickly how this will go. We'll have 3 for the first value for responses times 3 for the second value, so we should have a total of 9 responses. Okay, let's go ahead and quickly go through these 9 responses. Okay, I will blast through these and so for folks who are wondering about how I'm computing this, just keep that in mind. Okay. Here, so we have this cut 2, 3, 4, 5, and we'll keep going through this. Okay, so obviously we have yes, no, yes, both. Obviously, we're going to have no yes, no, and finally, no both. And you can probably take a wild guess what the last 3 are going to be, which is going to be our our last 3 values when it comes to both being the first input. And we can obviously make this very quickly and say do this, that, and let's see this here. This is going to be both yes, both no, and both. Okay. So we have a total of 9 combinations. Okay. Because of product types and being the Cartesian products and sum types being kind of like the additive product, inhabitants, this is kind of pretty straightforward to actually go and compute, okay, for simple types. For the case of something that goes from response to response, which goes back to our f example, let's say we have a function f that takes in a response and returns a response, we have to think about now essentially 3 cases for every possible thing. Okay, so for yes, no, and both, we're going to have to compute yes, no, and both. So, and different variations, right? You can have, and think of it the best way to think about this is like binary. Like if you're doing, if you're computing like an n-bit number, you like say 3 bits. You have 3 bits.
you have to include 0, 0, 0 and 1, 1, 1, and everything in between is obviously going to be incremented. So, if we're, in this case, we're going to be essentially doing 0, 1, 2 instead of a 0 and 1. Obviously, we're going to have to handle all three of those cases as we go up the chain to the final value, which is both, 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 okay, inside this link. So let's just go through a quick example here. Let's say that we have this, and we do, we start with f yes equals yes here, f yes, and no equals yes, and f both equals yes. And this is our first case here. Obviously, we can, check out the next one, and you could probably take a wild guess here that we are going to have to do yes equals yes here probably, f no equals yes, and we're going to have to probably deal with also and we're going to have to make a different calculation for this, a different function for this, when since we handled all three cases there. You could probably say this is going to be a G that takes in a response, okay, and we do G yes equals yes, G no equals yes, but G both equals no, okay, so either or. And you can keep going through this for each one of these all the way up to both, both, both. So now, sorry, 1 second. Okay. So now, how do we calculate the number of these invalid type signature? 1 second. What did I do? Oh, hold on. Let me change this to func response. And let's change this because it has to be lower. Actually, let me just lower this. Let's do RF. There we go. And let's do RG. Okay. We're good. Okay. So we have obviously this way of calculating all three. Okay, so just to complete this, first iteration that takes in a response, we have yes equals yes, no equals yes, and both equals both. And now we can go and update our calculation to the next line, and we can keep going through. Okay, and this is just a base 3 like calculation, if you really think about it. So the next step, obviously, that we can handle is how do we calculate the number of inhabitants? Well, the number of inhabitants here is we know that there's going to be a total inhabitants can be calculated. We know that response has 3 values, okay? And since there are 3 places that we're computing, okay, we have 3 responses, 1 for each thing. You can think about it 3 places. You know that then there are 3 possible values for each place with repetition. So this is your basic number of permutations that you can actually calculate, right? So this is going to be 3 times 3 for the second place, times 3 for the third place. Well, now since all of these are the same base, this is equivalent to 3 cubed, which is 27. So you can go through the exercise of expanding this, but this is how I've been kind of like thinking about this. So the reason why it's the exponentials is because of the fact that we are dealing with mappings
of every possible input to every possible output. We are not just talking about the number of valid the number of inputs to outputs that are valid with respect to the logic, okay? When you're dealing with types, and this is like a lesson that on all types and types design, when you're dealing with types, okay, you need to think about type membership as being not valid type membership. It's whether or not it's a valid type, not whether or not it's a valid output to your program, okay? And valid types means that the type instance adheres to the properties of the type, not necessarily to the logic that's within your program, okay? That's what makes a sound type. It has certain properties that in order to be something a valid instance, it's going to actually be it's going to have these properties upheld, okay? So in order for a type instance to be a valid instance of this type, it needs to hold these properties, and if it is, that's fine. Whether or not that specific type instance, okay, which is a value at the term level, is going to be a valid value to the output of your function, that's a different conversation, okay? But is it adhering to the properties of your type definition, in this case, the function definition that you provided? If so, it is technically a valid output, and in valid case, you need to consider it. Does this make sense for folks?
Yes, it makes sense to me.
Okay, cool. Thank you. So let's skip a little bit on expanding this version. I'd leave this kind of exercise of computing every single possible value of this to you folks to try out later on. Just simply write it out, and I think if you write out all of it and count it, you will see how quickly it is. It can go. I could simply just show you, you know. It's going to take a few seconds here. I could show you all the cases without having to write the type definitions. It takes a little while to write up all the function definitions for the patterns, but basically you have YYY, YYN, YYB, okay, and now you can go up to YNY, YNN, YNB, and then you can keep going to the final one. YBY, YBN, YBB, and this is the first iteration of just for all the Y's. And now we have to come, and if you see this, we have 3 for each value here, right? So that's a total of 9. We just computed the first one, right? And then obviously we have the same exercise for the other ones, and this. If you write out all the cases, you will see just very quickly that there'll end up being 27 combinations for this. So let's talk about higher kind of data types. Kinds for type has I've mentioned, and what the book mentions was something along the lines of being like a. I still hate the definition for this, but I can't think of another way of explaining it. It's the types of type constructors, all right, and which is nothing more than literally it's an encoding in Haskell or in I think I'm not sure how it maps up to. Category theory just yet, but my understanding that like I discussed last time, is a kind is nothing more than whether or not a concrete instance has been created. The default kind in Haskell, as we all saw, is the star operator, which means that the type has been fully realized. Okay, if the type has not been fully realized, as we saw before, we have this kind function, which essentially says, okay, I need you to specify a concrete type, and I'll give you a concrete type. Okay. Obviously, since this is a function, you can actually have multi-argument functions, which means technically you can have multi-argument type constructors. Okay, that requires different types of type constructors. Okay, and we've already seen this example here with either. Okay, either takes in two concrete types and returns a concrete type. Okay, this notation here is what's called a higher kinded type. Okay. Higher kinded types are pretty regular in Haskell. For example, Haskell itself considers lists, which we've been using up until now, to be a higher kinded type. And we'll be discussing why that is in a minute. But I want to discuss just this notion of why it's important to get comfortable with this concept, because although the book gave an example, a concrete example of a library that the authors wrote based on for Elasticsearch called Bloodhound, I didn't quite see, since it only requires a single type to construct the actual results, where the higher kinded piece is coming from. But of course, we can come up with, I think a better example here is what we've seen with either, because either here is nothing more than a higher kinded type that can be partially specialized, which means you can actually go and construct it and create type function families that handles different versions of specializations for the higher kinded type. The best adoption of this can also be used for those of you coming from other languages, because there are certain languages that give you this kind of flexibility. The best one that I can think of off the top of my head is C++ templates. I think if you actually think about template type parameters as being full type parameters, technically the template, whether it be a function class or alias template, is in essence a kind, right? And how you structure that kind is based on how you instantiate the template. Obviously, with partial template instantiations, you will get some code generation errors based on the fact that the template isn't fully realized. But if you end up fully realizing it prior to compilation, it is in essence the same idea that this kind idea is giving you, right? The main thing to note, though, is with partial specialization for higher kinded data types, okay, much like partial function specialization, okay, these are essentially placeholders that consumers of your API have to fill in order for, in this case, types to be constructed and type correctness to be preserved for your program, for their program, because they're consumers of your API. But additionally, in the case of higher order functions that take in holes, or even it allows you to provide hooks that could be functions themselves that would better customize the behavior. So let's revisit list, okay? Now, I earlier mentioned that list is polymorphic, and we've kind of discussed how it is polymorphic. As you can see in the definition of of the data constructor as illustrated here. Sorry, here, okay, as indicated here, this is essentially taking in a type variable, and it only realizes the type variable when the type is actually provided, okay? Let me show you what I mean by this, okay? If we pass in the empty list here, okay? And I know for folks who are directly following along in the book, I might be jumping around a little bit here, but I think it's important to understand this when we're playing around with the REPL, that we should, kind of go in and actually really dig into some of this stuff when we're dealing with types in the REPL. As you are developing your programs and you're developing your software, understanding the type signatures as indicated by the REPL will be important to understanding how things will get compiled if you choose to actually go and do GHC versus actually GHCI in terms for interactive design. Obviously, when you're deploying, you're going to have to do GHC, which in most situations is going to be actually invoked by whatever project definition you use, whether it be Stack or Cabal, to build your application. We'll touch base with those toolings in a later episode, but I just want to briefly mention it because the fact that when you're interactively building up your prototype, type signatures in your code are your friend, and inquiring about the type signatures as inferred by the Haskell REPL will, do you a lot of favors when you're using this programming language. And it's important that you get into the habit of actually inquiring what was inferred on this particular type definition versus what you've defined, okay? Because it might be the case that when the one that you're defining is probably less restrictive than the one that Haskell inferred, which is probably a good thing to know. So if we look at the type of the empty list, we can see that although it was constructed, okay, it is still technically a data constructor, a type constructor that has not been fully realized. So if you do the kind of this, you could see that this is a function. Now, if we go and cast this, okay, as being an int, okay, you could see immediately that this has now been casted as saying that this can only take integers. So now this empty list, if we go and do this, and we ask for the kind of it, as far as the REPL is concerned, one second. Perhaps you didn't use kind signatures. Interesting. Hold on a second. Looks like it is not liking the fact that I'm trying to restrict this, but we'll see. Yeah, it looks like I cannot restrict it without adding an additional thing. Let me see what other way we can actually handle this. Well, we'll see an example of this when we try and expand on a different definition of kind. Actually, we could do it this way. We see that in this list, that's right, we see that in the type signature of this list that the empty list is of type integer, all right? The kind that we're getting is actually the kind of the list of integers, which is obviously a concrete type, okay? Again, we passed in the variable into the polymorphic list constructor and the type variable specifically. But at the end of the day, this type constructor itself is only fully realized when the integer construction was provided. Okay, whereas with the empty list, when we casted it, that's when the type construction actually completed, and you also got the list being an integer, okay? So in this type example here, we are actually doing type construction after the cast. Here, we're doing it right upon providing the fact that we have an integer, okay? So those are two different steps there. The cast has to occur for the construction to actually complete itself, which will then allow you to pass in the empty list into, say, a function that requires you to pass in a list of integers, for example. The reason why it's important to understand this, and again, if we look back at the definition, we have also this data constructor that doesn't take in any arguments. This nil constructor is a special value that, if you recall, represents the end of the list. We need, obviously the single type to be provided in order for a concrete construction to occur. But there's one thing unique about this particular definition for list, okay, and that is the colon operator or cons operator, okay. We know that this is an infix data constructor. Up until now, when we talked about data constructors, okay, especially when dealing with type algebras and some types and product types, the majority of our data constructors have been prefix data constructors, okay? But technically speaking, you could define a infix type and an infix data constructor, right? So an infix type constructor and infix data constructor. Operators fall into this category, okay? Non-alphanumerics operators specifically are infixed by default, as you may know. And we've looked at a lot of non-alphanumeric operators already. All the arithmetic operators, as well as the relational operators that we dealt with for dealing with equality, are all examples of non-alphanumeric operators that are infixed by default, okay? Additionally, we've also looked at a couple of alphanumeric operators like div and mod that are that can be used in an infix way, but are prefixed by default. Okay. When you're defining a type constructor in this way, and we're trying to define it as an infix constructor, you're going to have to define it to start it with a colon. Okay. This is actually just a requirement by Haskell, apparently. I didn't quite get why, but apparently infix operators for infix types and infix type constructors or infix data constructors, they all must start with a colon. Now, I've been trying to look for another example of an operator that is infix that uses a colon, but I could not find one. Let me see if I could just do this quick Google here again. See, maybe I just missed it. But it looks like someone also said that this might be an old Stack Overflow article, because the but okay, so this is a little nuts, but the way to do it is you need to actually use an extension, just like we had extensions here before with language, generalized new type deriving, and generalized flexible instances. The way you do this is with the type operator extensions. And once you provide type operator extensions, now you can actually define these infix type operators that have a colon thing. All right. This is very important. Here's the quick example. I'm getting this off of This is from and obviously when we're using these infix operators, number one, they're non-standard, all right? They're not, the infix operator extension is available in GHC. It's not part of, apparently it's not part of the Haskell 98 report, so the Haskell standard may not necessarily have it, but although I'm probably going to put my foot in my mouth and get shunned by a lot of Haskellers here. I really don't know of another active Haskell compiler or reference implementation other than GHC. At some point, I knew two. There was Hugs and there was GHC, but I think GHC kind of like wiped that out, into oblivion. It might still be there, but I don't know of anybody who actually uses it. Those of you who actually implement your own Haskell replicas and Haskell implementations, which I encourage, because Haskell itself is a language specification, okay, it isn't GHC. Just bear in mind that there are these Haskell extensions that some folks might use to get some better flexibility in the language, all right? So let's see a quick example of using this extensions. We do example of infix type constructors, all right? Let's do this nuts example, okay, of taking addition, all right? Okay, let's say that we have this data A plus B operator, all right? This is now infixed. And now the infix data constructor and data constructors, infix, type in infix data constructors. Now with the infix data constructor, recall that this is going to have to start with a colon, okay? So now, according to the type operator, this is valid Haskell, okay, the type operator extension. If you did not do the type operator extension, this is what you're going to get. Let's go ahead and see what the error is if we don't have the type operator extension, shall we? If we try to load this, you're going to get illegal declaration of plus, okay? And it explicitly says use type operators to declare operators in types and type declarations, okay? So now that we have this crazy thing, we can now use this type in something. Let's define a function f prime, okay, that takes in an a plus b and returns a, for example. And we'll just say a. Now we need to pass in a data constructor, and this is going to be a. And we can do a g prime that takes in an a plus b and returns a b, and this guy can actually take in, g prime a colon plus b equals b, okay? And now that we have this ability here to pass in anything, and just to show you, let's try f prime 5 plus 4 and see what happens. Use flexible context. Okay, I may have to actually provide this in the REPL. Give me a second. I don't know if I can do it this way, but we will see. Okay. Okay. Provide that. Language, flexible context. Let's see. Okay, and let's do f prime 5 plus 4. Let's see what happens. Right, it is not. Oh, my apologies. I'm not constructing it right. Let's do this here. This is going to be 5 colon plus 4, like this. And if I do, d prime, let's say, a plus colon 6 or something like this, you can see that it's going to get it, and we can actually use these infix type operators, these infix data operators to construct things. So that's pretty neat. If you look at the GHC documentation, type operators actually provides a couple of interesting, well, I think this is actually examples that are provided in the documentation for the Glasgow compiler for language extensions. They provided a couple of examples that you may want to leverage or take a look at for defining types using the type operators extension. I'm going to defer you to the GHC GitLab documentations on type constructors, infix type constructors, section 6.4.3 for more information. I'm going to pause a minute so I could just take a quick drink here. In the meantime, if there are questions, please post them in the live stream chat, and I'll get to them. All right. Okay, looks like we don't have any questions, so I will move on. So the last topic that we're going to be kind of discussing is kind of an example, a case study that kind of culminates all the stuff that we've kind of discussed thus far. That is implementing a binary tree inside Haskell. Okay, the reason why a binary tree is a natural, succession to a list is because the definition is very, very similar to a list. Okay, and most people know what a binary tree is. If you don't, I suggest you go and read up on the Wikipedia article on the binary tree. We know that that binary trees is nothing more, and this is straight. This example is in 11.17, and we're just going to work out through it because there's a lot of not everything in there is in the Haskell book. Not everything is in there. Just some of the basics are provided, and some of the type definitions. So we're going to just kind of fill in the gaps of what the book provided in this example. Okay. So what is a binary tree? First off, so we know that a binary tree contains some values inside of the top of the tree, and say it contains 2 children at each level until you're at the leaves levels, right? But what does that mean? Okay, when we go and define it. Okay, so we define a binary tree of type A to being either a leaf or a node that contains a binary tree of type A on the left side. This is known as our left subtree. The actual value at the current node, and a binary tree of type A on the right side, which is known as the right subtree. All right. This itself is the definition of a binary tree. Notice we did not have to define what, just like everything else for the data construction, what a node is, what a leaf is. Those are data constructors that are automatically set in stone for you. Okay. At each level, we have a value of some sort of type. Okay, at each node. Okay. When we're constructing the nodes the first time, you're going to end up asking yourself, well, what is a leaf in this case? Okay, think of leaf as being nil. All right. You could certainly have named it nil. I'd rather you don't, just because of the fact that I think this definition is much more clear for folks who are first learning for binary trees the first time, because the leaf data construction essentially indicates that there's nothing provided. It's a nullary data constructor. Okay. When you normally think of leaves in other contexts, normally the leaf definition is that it is a node that contains two nil subtrees. And that's represented as a leaf. In a sense, because leaf is a nullary constructor, this is the same definition as your normal C definition. Okay, but if you're getting confused by this just by doing so, by all means, go ahead and correct it for your own understanding. Okay. Because trees are structured this way, we know that we can actually leverage search a little bit more. Well, not even search. Retrieval and structuring actual data is a little bit more efficient. Okay. Obviously, you can minimize the number of accesses to actually access particular data, because it's now a logarithmic access than a linear access in the case of a list. But again, this is all basic stuff for data structures. Let's talk about insertion. Tree insertion and list insertion in Haskell, and I know I'm probably beating a dead horse here, are the same. Okay, in the sense that the idea is at least the same. We are dealing with an immutable list before. We're dealing an immutable binary tree in this case. Okay. One thing to be aware of when you're dealing with a binary tree, especially if you're dealing with a binary, we're going to probably make a BST here, is we need to have some sort of information in order to actually figure out how to actually insert those values into the tree. The example in the book kind of picked that, well, the best thing to do is just go ahead and, do the insertion based on ordinal, right? So this will give us the relational operators, okay? So let's define our function here as inserts into tree. I know I'm making this a little bit longer than what the book says, but insert has its own connotations inside of Haskell. Specifically, I think insert has actually, you know what? You could probably just use insert. Let's just do insert here. You know what? Yeah, we'll go ahead and do that. This way, we can use the type definitions later on. Okay, so we have our insert. This is our binary tree insert. This is going to take a type A that has to implement the ordinal operators. Remember, those are the relational operators. And then this is going to then return us a function that takes in an A and a binary tree A, and it's going to return a binary tree, all right, of type A, okay? This is the reason why it's written this way is because the first argument is going to be the value that we're going to insert into the tree. The second argument is going to be the tree itself, and the third argument is going to be the actual reconstructed tree. Because every time you go and insert into a tree, you're always going to create a new tree. Again, Haskell's values are all immutable by default. Okay, there is no way to actually go and change them. So how would we go and construct this? Well, obviously we could just have two cases. The first case is we're inserting into a empty tree. Well, what does that mean? We're inserting into a leaf in this case, all right? Well, if we have this, well then obviously we're creating a tree from scratch, which means our insertion is going to be a node with the value B that contains a left subtree that's a leaf and the right subtree that's a leaf. This is what I was talking about earlier. This is essentially the definition of a node with 2 nil subtrees. Okay. The second definition is a little bit more the case that we need to start thinking about. Okay, the first one is going to be, you have a node, okay, that has a left subtree, a and a right subtree. Okay, this is going to be a recursive definition, but we're going to go ahead and do this with a simple case. Okay, so this here is going to have 3 cases. Okay, the first case is b equals a. Okay, remember this notation when we're using or here, we're essentially doing like a case switch between the two. And we have the first case here where b equals a. Well, if b equals a, we can always just replace b with a because they're the same damn thing. So here we're just going to go ahead and say, you know what? Don't necessarily insert it. We don't want repeats. Okay, if you want repeats, you can decide in your example application how to which subtree that you may want. Here, we're just basically saying since they're the same, that means we're just going to assume we've inserted into the tree already. All right. Now we have 2 cases here. We have b is less than a and b is greater than a. Okay. When b is less than a, since we're going to be using kind of like a binary search tree, we know that we can actually have to insert prime b into the left subtree, a, and then the right subtree is left intact. When b is greater than a, obviously it's the exact opposite. Node is going to take the left subtree intact. We provide a, and then we're inserting b into the right subtree. Sorry, insert b into the right subtree. This actually now constructs our thing. Oh, sorry. I did this. That's what I mean. My apologies. Okay. There's some warning here. What is the warning? Insert node leaf leaf. Okay, so that means we need to provide. Okay, so we need to provide a case when there's nothing provided into our leaf. So let's do that. Insert. Let's do this at the bottom here. I'm a little afraid that if we don't put the right default case, we're gonna get screwed. Leaf equals leaf. Okay. So if we don't, let's see, do this. This is going to be overlapping patterns, but if I do this, redundant. Let's see here. Oh, okay. Incomplete patterns. Patterns not matched. Node leaf leaf and node nothing else. Oh, okay, sorry. So I misread this. It's if we don't have Oh, got it. It's because it cannot recognize the fact that this will handle the left subtree and the right subtree. It's kind of assuming that these are there and just not recognizing that this section will actually handle that. Let's see this. Let's try this. Insert 5 into a leaf. We got an empty list. Let's do base tree with this. Insert 5 into a leaf. Okay, so now base tree has what we have earlier. Now let's try to insert 4 into base tree. What happens? We see now it's going to try and insert it into there. We try to insert, let's go ahead and do this. Base tree equals insert 4 into base tree. Obviously, doing this is not overwriting it. It's constructing a brand new tree and just assigning the pointer to base tree. All right. Wait, did I mess that up? Yeah, I think I may have just locked. Yeah, I may have locked Haskell. Did not realize that was going to screw me up. Okay. Give me a second here. This is going to be a simple fix. We're just going to temporarily switch out. Let me start up a new thing here. Not right now. /9 Emacs. Okay. Let's do this here. And do an Emacs and W. Give me a second here so I can actually share this with you folks here. Okay, so let's see if everything is good. Let's share this with you guys. Okay. Okay. And okay, so let's reload our project here. My apologies, folks. Thought that would actually give me some notion of Haskell projects tutorial. Maybe I keep forgetting that in Emacs we have different, slightly different interactions than when I'm using normal the normal terminal. Okay, so let's go back to what we were talking about earlier. And 1 second to my friends here. Let's this. So as we started out, we had our insert 5 into a leaf. So we have our leaf, and now we have insert. Let's do another tree equals insert 4 into base tree. Now another tree actually now contains that, and we haven't actually talked about how to actually extract the other things. So the next logical thing is now that we have a tree here, and we actually have some notion of this, and we could see once again if we go and insert 6 into another tree, we'll get 4, 5, 6, obviously in that order. Okay. But we haven't actually figured out how to map to each of these. Okay, how do we go and construct this? How do we end up leveraging this? Okay, we want some way of traversing through this, right? So one way of doing that is obviously implementing the map structure for and what I mean by map structure, I mean a map tree function. We want some way of obviously transforming this map. Okay, so let's try that. So we're just going to go through this simple example of map, and then there are a couple of other examples that I think you'd probably have fun with if you just understand this example. That's building up pre-order, in-order, and post-order traversals functions and things like this using pattern matching. But the map one is particularly interesting for me because I like kind of like this transformation kind of stuff here. So I just thought we just go through this example of mapping a function into a binary tree. Okay. Now, map tree is what the function is called in the book. It takes in a function. Okay, this is kind of the exercise they wanted us to go through. The binary tree that we're actually inserting, and it's going to return a binary tree that we are of type B. A and B could be the same, but it may not be. All right. So now we have kind of the base cases. So let's create our test tree, for example, okay, just to make things a little easier. We already have our test tree written down here, but I'm going to make it a little bit cleaner just for kids, okay? So we have our test tree, which is a binary tree of integer, okay? And our test tree is equal to node leaf for leaf. We have 5. Okay, and we're going to go ahead and put it, in the order in which we expect it to, and node leaf 6 leaf. Okay, let me just define this later here, and let's go ahead and do this for right now. Make sure that I did not get any errors. Okay, so we're good. So now we're going to go ahead and start with our first thing. Well, the first thing that we need to think about is if we pass in, say, anything into a null tree. Obviously, if we're passing any function and we have a leaf, we're going to return a leaf. Okay. Now, there's going to be a couple of cases that we need to go in and kind of define, okay? The first one is, so the second pattern is going to take 3 arguments, okay? It is, the data constructor specifically takes in 3 arguments. If you actually look at the data constructor of the node, this is actually a function that takes in a binary tree, and the data constructor returns an A and a binary tree on the right side and a binary tree on the left hand side. Okay. So you need to pass in, okay, into this function several types of patterns that you need to leverage, okay? The node needs to return, obviously, a value of type P and binary values with type A inside them. So the way you can do this is, let's say that we have map tree we have F, and we need to provide, the first case is going to be obviously node leaf Node left. Here we go. This. And this is just going to be map tree map left. Okay. So if we have a left subtree, we're going to go and map into the left subtree. Let's say we have obviously let me see, two functions, one gets you, the other maps binary trees. Okay, so let's try mapping these things out. So the first thing is we have a left subtree, and it doesn't have, oh, I got it. So we need to write, if we hit a leaf and we don't hit a leaf, okay? So, I did this wrong here. So let's go this again. There's two cases. One is we have tree, f, node, leaf, a leaf. In which case, you just simply do node, leaf, fa, leaf. We have our map there. Our second one is going to be map tree f node left b, and let's use b here for a b is going to kind of screw things up, but it doesn't matter. We'll see what happens. Right. In which case here we have to do a node. We just called recursively map f left, f b, map tree f right, and this should just take care of all of that. Let's see what happens. Okay, everything got compiled, and I have this underlined for some reason. Warning, binding is some existing. Oh, shoot. Let me do something here, because I hate shadowing functions. Do I have an F here? Yeah, I do. Let me go ahead and do this. And comment region and Q. So now we have this. Good. Let's try to map ID, because I think ID is a fun. The type signature is ID A to A. Map ID to test tree. What happens? Could not match expected type B with actual type binary integer. In the second argument of map, mainly test tree. Oh, sorry, not map. Map tree. And we got our first things. Obviously, that looks good. Let's go and check this guy out here. Let's do map tree lambda x times 2. And let's do test tree again. And we get 8, 10, 12. So we now written in a very simple thing. We did not write any, crazy things here. We just simply wrote, if we hit a leaf, go ahead and just generate a leaf. But if we hit a subtree, go ahead and call map tree on the subtree, on the left subtree. Go ahead and transform the current value and go ahead and then map on the right subtree. And then it will go ahead and structure this. And it doesn't matter how you structure this, you end up going through this pretty quickly. So that's what I had to cover today. Of course, we can spend more time writing some of the other exercises that the book provided, like converting binary trees into lists using those patterns. But those are all exercises in pattern matching that I think it is important that you get some experience and actually understanding on how this kind of structure kind of works. This is some of the stuff that I have been playing around with a little quickly. But the main thing to recognize and take out from today's exercise and implementing some of the basic things is the fact that once you understand the structure of your types, okay, especially when it comes to algebraic data types, the pattern matching rules just kind of fall out into based on the structure. Function types are a special type because they are a mapping that represents outputs to inputs, which means there is a set of outputs to inputs that you can consider and should consider when you're building up your designs. And finally, lists themselves are polymorphic type, and they are specifically a kind type, but they are not a higher kind. And well, there's an argument that they are a higher kind of type, but we did not see that here. And in fact, if you end up looking at the kind for a list, it's actually a regular kind. It's not a higher kind type. It's not requiring to do different things. So I would like folks to comment on this in the YouTube comments, or folks who are more knowledgeable than I, to kind of step in and kind of like, say, yeah, this is why it's a higher kind of type inside of Haskell, because the book explicitly calls this out, and I'm not entirely sure why. That lists are a higher kind of type, but that's something I'm going to have to dig into, and maybe next time when we cover some other stuff before we start, we can cover this particular piece. So that's it for today. Thank you for joining. I appreciate you guys, taking the time out of your Thursday evening to check out AFP's Haskell study group. And those who are watching this later, I appreciate you taking the time out of your day, whatever day of the week it is, to go and actually watch the Haskell study group. Next time, we're going to be covering Chapter 12 in the Haskell book. Folks who are reading Learn You Haskell or Real-World Haskell, my apologies. I don't quite know where this particular section it matches into that world. So when we kind of look into a couple of things, and as I work through this chapter a little bit more thoroughly, if there are some particular things, I will go and post in the comments in the meetup announcement, which should come out tonight. Those of you who are part of our meetup, and if you're not part of the meetup, I encourage you to join the Atlanta Functional Programming meetup. You can then get these kinds of announcements, these kinds of messages too as well. So, and before I let all of you go, of course, Atlanta Functional Programming is an organization that's dedicated to kind of promote and show off functional programming as a whole, regardless of language. We are language agnostic. And we are in search of speakers. If you have a topic in mind for functional programming that you'd like to highlight, whether it be a particular library you wrote for a language or so forth that is implementing a functional architecture or so forth, drop us a line. I'm available on both the Lisp Discord server as well as Functional Programming Slack and Tech 404 for those of you who are in the Tech 404 community. Shout out to that community. And let me know your idea, and we will put you in the schedule. We have yet to determine our venue situation. When we are at any point in time coming back, we will announce it and let you know when those talks are. Until that, in the meantime, the majority of our talks will be available both on YouTube and our YouTube channel. And if those of you are interested, you can also join us for a live chat running on Hangouts simultaneously. So I will hope you all have a good evening, and